My dear students, in my previous video, we discussed about the algebraic operations on complex numbers. That is, addition of two complex numbers and subtraction of two complex numbers, Z1 and Z2. So in this video, we are going to see the multiplication of two complex numbers. Multiplication of two complex numbers. If Z1 is a complex number x1 plus iy1 and Z2 is a complex number x2 plus iy2. Multiplying these two complex numbers Z1 into Z2 is equal to x1 plus iy1 into x2 plus iy2. See, in your lower classes, you multiply in algebra a plus b into c plus d. You multiply like that, two terms, a plus b into c plus d. So using the same idea, we are going to multiply here x1, x2 plus I into x1, y2 plus I into x2, y1 plus I into I square into y1, y2. This is x1, x2. I square is minus 1, so minus y1, y2. Here, this is the real part. Imaginary part is you have taken that common I outside. x1, y2 plus x2, y1. If you take that I as common, you get x1, y2 plus x2. This is the multiplication of two complex numbers, Z1 and Z2. See, using the same idea, I am going to solve one example, multiplication of two complex numbers. That is Z1, say a complex number 2 plus I3. Z2 is a complex number 1 plus I4. Multiplying these two, Z1 into Z2, that is 2 plus I3 into 1 plus I4. You consider this is x1, y1. x1 is 2, y1 is 3. x2 is 1, y2 is 4. Using the same idea, you get x1, x2, 2 into 1, x1, x2, minus y1, y2, minus 3 into 4, plus I into, this is the real part. Now imagine part I into x1, y2, 2 into 4, 2 into 4, plus x2, y1, 3 into 1. Like that you multiply. Your answer is Z1 into Z2 is 2 into 1, 2, minus 3 4s are 12, real part, plus I into imaginary part, 2 4s are 8, plus 3 1 is 3. So, minus 12 plus 2 is minus 10, plus I 8 plus 3 11. This is the product of Z1 into Z2. So, like that, you use the multiplication idea of two complex numbers. This is another algebraic operation. Addition, subtraction, this is multiplication. Okay. Now, I am going to recall an idea which we have seen in the previous video. That is, if a complex number Z is multiplied by an imaginary unit I, the geometrical meaning of the multiplication of a complex number Z with an imaginary I is the rotation of the complex number Z about the origin through an angle 90 degree or pi by 2 radian. Okay, we will pass on to that idea because we already seen the geometrical meaning of that multiplication of a complex number Z with the imaginary unit I. We have seen in the previous video. To the extension of that idea, I gave it as a note. If a complex number is Z is multiplied by imaginary unit I, consider this is x, real axis x, this is your imaginary axis y, this is origin. Suppose this is the complex number Z. If Z is multiplied by the identity, imaginary unit I, its geometrical meaning is this Z is rotated about horizon in the counterclockwise direction. Counterclockwise direction is otherwise called anti-clockwise direction through an angle 90 degree or pi by 2 radian. See, this is the geometrical meaning of a complex number Z multiplied by I. Rotation of the complex number Z about the origin through an angle pi by 2 radian in the counterclockwise direction. Similarly, again if you multiply by I square is Z. This is I square is Z. I square is Z. I square is Z is again rotation of the complex number I is Z about the origin through an angle pi by 2 radian is the geometrical meaning of I square. If you multiply by I is Z with I, it is I square is Z, it is nothing but again rotation of I is Z about the origin through 90 degree in the counterclockwise direction. And I cube is Z. This is I cube is Z. Here also the multiplication of I square is Z in the counterclockwise direction through an angle 90 degree in the counterclockwise direction is I cube is Z. I square is Z. If you multiply about origin to 90 degree in the counterclockwise direction is I cube is Z. Again I power 4 is Z is same as I is Z because I power 4 is 1. 1 into Z is again same as Z. So it is also I power 4 is rotation of I cube is Z through origin about an angle 90 degree in the counterclockwise direction. This is what I am going to give in this video. So remember this. This is the idea of rotation of the complex number Z in all the 4 quadrants. First quadrant is Z, second quadrant is I is multiplication of I which is Z, third quadrant is I square is Z, in the fourth quadrant I cube is Z you get, again I power 4 is Z is again in the fourth quadrant, which is same as Z. That's all about this idea. Now we will go to the exercise 2.2. Exercise 2.2. We have in the first problem you have 6 subdivisions. Exercise 2.2. In this exercise we have some 6 subdivision in the first problem. First problem. Evaluate Z plus W if Z equal to 5 minus 2i and W equal to minus 1 plus 3i. Minus 1 plus 3. It is given. Evaluate Z plus W. If Z is 5 minus 2i and W is 5 minus 3 plus 3i. It is simple. Z plus W is simply you have to add these two. 5 minus 1, 4 plus 3 minus 2 is 1. So 4 plus I answer immediately we can say by seeing this problem itself. But we have to solve 5 minus 2i plus minus 1 plus 3i. See, real part 5 minus 1 plus I into imaginary part minus 2 plus 3. 5 minus 1 is 4. 3 minus 2 is 1. 1i is I. This is Z plus. This is the first problem you have. This is the first subdivision. The second subdivision they ask you to find out Z minus IW. Second subdivision, evaluate Z minus IW. What is Z? 5 minus 2i. Z is 5 minus 2i. Minus I into W is minus 1 plus 3. Simplifying, you get 5 minus 2i. You multiply with minus I into that W, I get minus into minus plus I, and plus into minus minus 3i square. So real part is 5. I square is minus 1 into minus plus 3. Minus 2i plus I is minus I. Minus 2i plus I is minus I. 5 plus 3, 8. 8 minus I is the answer for Z minus IW. This is the second subdivision. Third one is evaluate Z plus 3W. See, I will give this sum for your practice. You know Z is 5 minus 2. 2Z is, you multiply Z by 2, that is 10 minus 4i. 3W, you multiply W by 3. Multiplying by 3, you get minus 3 plus 9i. And you just add, you will get the answer for the problem 3. Okay? So you try to solve this problem by your own. Now I am going to fourth subdivision. I hope you understand. Now I am going to erase this sum because I am going to solve the next subdivision 4. Fourth one is ZW. Z into W we want. ZW, the fourth problem is given Z equal to 5 minus 2i and W equal to minus 1 plus 3i. Evaluate, fourth one is ZW equal to 5 minus 2i into minus 1 plus 3i. As our multiplication principle, just we have seen in the beginning, x1, x2, 5 minus 1 into minus 1, x1, x2, minus y1, y2, y1 is minus 2, y1 is minus 2, y2 is 3. Y1 is minus 2 into 3. Think this is the real part. X1, x2. X1 is 5, y1 is minus 2. X2 is minus 1, y2 is 3. Therefore, x1, x2, 5 into minus 1. Minus y1, y2. Y1 is minus 2, y2 is plus I into x1, y2, 5 into 3. Plus x2, y1. X2 is minus 1, minus 2, y1 is minus 1. So this is again 5 into minus 1, minus 5, minus into plus, minus 2 3s are 6, real part, plus I into 5 3s are 15, minus into minus, plus 2 1 is 2. That is 6 minus 1 is 1, plus 15 plus 2 79. This is your ZW. This is the force. Okay. And shall I pass on to the fifth sum? What is the fifth sum given? See, evaluate. Fifth sum is evaluate Z square plus 2ZW plus W square. They ask you to find out Z square plus 2ZW plus W square. What is Z? 5 minus 2i the whole square plus 2 into ZW. In the fourth sum we determine ZW. We take the value that. But in the example, you try to solve once again. If the sum is asked separately, you have to find out ZW separately. But here, I have ZW here. So this is 2 into ZW is 1 plus 79. Plus W square is what? Minus 1 plus 3i the whole square. So this is our requirement. This is again a minus b whole square. You know a square minus 2 into a. A minus b whole square is a square minus 2. A is 5. B is minus 2i. Sorry, b is 2a. No, not minus 2. Because a minus b whole square. A square, b is 2a. A square minus 2ab plus b square. B square is 2i the whole square. Next, plus 2 into 1 is 2, plus 17 into 2 is 34i. Again, this is minus 1 plus 3i whole square. This is a plus b whole square. You consider this as a plus b whole square. That is a square. So ZW, you have 1 plus everything. So to solve this, I erase this. I erase here. So that I can solve the problem. I repeat. Z plus this is Z square. Fifth one is evaluate Z square plus 2 is W plus W square. Z square is a minus b whole square. A square, pi square minus 2 into a b 2i plus b square is 2i the whole square. A square minus 2ab plus b square. And this is plus 2 into 1 is 2 plus 2 into 17 34i. Again this is a plus b whole square. Again a square minus 1 square plus 2ab a minus 1 b 3i plus b square 3i the whole. Simplification, you get 25. 2 5s are 10, 10 into 2, 20i. I square is minus 1, 2 square is 4, so minus 4. This is plus 2 plus 34i. Again minus 1 square is plus 1. Here minus 2 into 3, 6i minus 6i. I square is minus 1, 3 square is 9. So this is 25 plus 2 plus 1. I calculate the real parts. 25 plus 2 plus 1 minus 4 and minus 9. 25 plus 2 plus 1 minus 4 minus 9. Right? All the real parts, imaginary parts are minus 20i minus 6i plus 34i. See 27, 28 minus 30. 25, 27, 28 minus 13 is 15. 26 plus minus 26 plus 34 is plus 8i. So 15 plus 8i is the answer for this expression. Z square plus 2 is W plus W square is 15 plus 8i. This is our fifth subdivision. Next one, sixth problem. In the exercise given, it is Z plus W the whole square. What is Z plus W the whole square? You know, by I plus B whole square is Z square plus 2ZW plus W square. So far, this is the right hand side is same as the problem 6. Z square plus 2ZW plus W square is same as Z plus W whole square. Therefore, instead of solving this problem, to solve this, you will get again 15 plus 8 is your answer. This is our sixth sum. Let's solve about the exercise. We will continue.